Now that we know how to get the sample using different sampling techniques, once we get our sample and we get descriptive statistics from the sample, and the most common to get it is our mean, the sample mean within that population, let's now consider it as a random variable. If we were to take a great many sample sizes n from the same population, we would end up with a great many different values for the sample mean as illustrated here. So if we get 5 samples, we will be able to get 5 different means. And the resulting collection of this sample means could be viewed as a new random variable with its own mean and standard deviation. So the probability distribution of these different means from different samples is what we call the distribution of sample means, or the sampling distribution of the mean. So, for any specific population, the sampling distribution of the mean is defined as the probability distribution of the sample means for all possible samples of that particular size. And what does it have to do when we get just one sample, and we assume, or how can we assure that it is actually a representative of the population? So here's how it works. Say for example, we have the random variable answer as actually number of soda cans in the refrigerator. There. So we have Bill, just have one soda can, Carl one, Denise, and Ed five. So if this is our random variable, and then so we do its probability distribution here on this side. So we have the values 1, 3, 5, and then its probability distribution now would be, since there's 2 ones, that's 1/2, and then we have 1/4 here and 1/4 here. That's why we have this table, this bar chart here that represents this table here. And for us to get our mean of the probability distribution, we form our third column, because again the formula for the mean in the probability distribution, that would be the summation. That would be the summation of x times the probability of x. So we get x times probability of x here, so that's 1/2, 3/4, and 5/4. Hence, we're going to get 1/2 plus 3/4 plus 5/4, and we're going to get there 5/2, or 2.5, which is what is stated here. So then when we're talking of populations, we get an expected value of 2.5 soda cans in our population. Now, if we get, say, all possible simple random samples of 2, we get the following. So these are all the possible simple random samples of 2, n equals 2. The sample size is 2. We have here, and then we get the mean per number of soda cans per specific person in the sample. So we get this one here. Now, the sampling distribution creates a probability distribution out of these means. So we can see that the different means that we get is 1, 2, 3, and 4. So we can create our probability distribution with these means. So now, if we create the probability distribution of our sample means, we do it here, then index. So we have the different values of our mean, which is 1.0, 2.0, 3.0, and 4.0. The probability of us getting a value of 1, we have this one here, that's just 1, so that's 1/6. The probability of us getting a mean of 2 would be 1, 2, so that's 2/6, or 1/3. The probability of getting a 3 is also example, 2 out of 6 or 1/3, well, the probability of getting a 4, that's just 1/6. So with this now in mind, we now get the mean of the sampling distribution, the expected value, which is again the summation of x times p of x. So here we multiply x times p of x here. So hence we get 1 times 1/6, that's 1/6, 2 times 1/3, 2/3, 3 times 1/3 times 1, and 4 times 1/6, that's 2/3. And if we are to add all of these, we're going to get 5/2 or 2.5, which you can see that the expected value or the mean of the probability distribution of the sample means is the same as the actual population mean. That's one concept that connects the sample to the population, that the expected value of the sample, of the sampling distribution on the sample is actually the population mean in itself. So the sampling distribution is one important concept in inferential statistics because it tells us how your sample can actually represent the population. Because if our sample follows the sampling distribution, then the expected value that we get is actually the actual population mean. So the sampling distribution of the mean will have the same mean as the original population. Now, the standard deviation of the sampling distribution of the mean is referred to as our standard errors. So how far your sample mean from the population mean is referred to as the standard error. Now, if the original population is normally distributed, the sampling distribution of the mean would also be normal. Hence, we would know some of its we will know its probabilities because we have studied the normal distribution already. Now, if the original population is not normally distributed, the sampling distribution of the mean will be approximately normal for large sample size and will more closely approach the normal distribution as the sample size increases. And this is known as the central limit theorem, and we were going to discuss that later on. So now to formally define the sampling distribution of the mean, where simple random samples from a normally distributed population, regardless of the sample size, the sampling distribution of the mean would be normally distributed with the expected value equal to actually the population mean. And the standard error would be the population standard deviation divided by the square root of the sample size. So the standard error of the sample means will be smaller than the original population because that would mean each sample mean is the average of the several values and relatively large or small values of x are being combined with those values that are less extreme. And since the sampling distribution of the mean is normally distributed, we follow our z-score formula. The sample mean minus the population mean. The sample mean becomes our raw score. And then the standard deviation here is our standard error. Now, this assumption of normality is not always realistic, since in many cases the population is either not normally distributed or we don't actually know anything, or we don't have knowledge about the distribution of the population we're studying. However, provided that the sample size is large enough, that is in our case, the sample size is greater than 30, then the sampling distribution of the mean can still be assumed to be normal, and that is the key idea of the central limit theorem. That for large simple random samples from a population that is not normally distributed, the sampling distribution of the mean will still be approximately normal and it still follows its characteristics, its descriptives with the mean of the distribution being the population mean and the standard error being still following this, as long as the sample size is large and simple random. There. As the sample size is increased, the sampling distribution of the mean will more closely approach the normal distribution. So even though the original population is not normally distributed, as long as your sample size is large enough, in this specific case greater than 30, then the sampling distribution will be normally distributed, and that would be enough for us to be able to have some conclusions about the sampling distribution of the mean. So take note that this is what I've already explained a while ago, that regardless of how a population happens to be distributed, the central limit theorem enables us as though the samples were normally distributed. And because of that, the central limit theorem is basic to the concept of statistical inference, because it permits us to draw conclusions about the population based on sample data without having any knowledge actually about the distribution of the population. Now let's have some problems regarding the sampling distribution of the mean. So we have number one. Let's move this here so we can so there. So we have in number one, a random variable is normally distributed with a mean of $1,500. There, and the standard is with a mean of $1,500 and a standard deviation of $100. Determine now the standard error of the sampling distribution of the mean for the simple random samples with the following sample sizes. So, recall that the standard error of the mean is given by the standard deviation divided by the square root of the sample size. So for letter A, we have n is equal to 16. Therefore, the standard error would be equal to 100 divided by the square root of 16. Without a calculator, we can easily solve this as this is 100 over 4, which is 25. On the other hand, though, if n is equal to 1000, then our standard error becomes 100 over the square root of 1000. Square root of 1000, and this actually becomes the square root of 10, or which is approximately 3.16. And as we can see here, the larger our sample size, this is very much larger compared to 16, the smaller our standard error is. The smaller our standard error is, the closer we say that the sample mean is to our population. Letter C and D, I will leave that to you as your own practice. Let's now go to number 2. There you go. Number 2 is a bit long, so yeah, let's extend it like this. A manufacturer produces safety pressure valves that are used on domestic water heaters. In the production process, the valves are automatically preset so that they open and release a flow of water when the upstream pressure in the heater exceeds 7 bars. In the manufacturing process, there is a tolerance in the setting of the valves, and the release pressure of the valves follows a normal distribution with a standard deviation of 0.30 bars. A. If many random samples of size 8 were taken, what proportion of the sample means would have a release pressure between 6.8 and 7.1 bars. So, if you're going to notice, let's place it here in 2A. By the way, before that, in number 2, we have our population mean of 7 bars and a standard deviation of 0.30 bars. Now, in letter 8, it doesn't ask us the probability or the proportion of the proportion of the population that would have release pressure between 6.8 and 7.1 bars. It asks us that if you take many random sample sizes of size 8, uh, many random samples rather of size 8, what would now then the probability that the mean of these samples would be between 6.8 and 7.1 bars? So it's now specifically asking in the distribution where the sample size is 8. If you take a lot of samples with sample size 8, what's the probability or the proportion of those sample means that they're going to have a mean between 6.8 and 7.1? So the first thing to do is to compute the standard deviation, because the standard deviation is what you would need to compute these probabilities because of the z-score formula. So first, your z-score formula is the mean minus the sample mean minus population mean over standard error. If you don't have the standard error, we compute our standard error first, which is actually 0.330 bars divided by the square root of 8. And this will then give us, I'm going to, the exact value of this is 3 square root of 2 over 40. But for the sake of computation, since we're going to use quite a lot of decimal places, let's use 4 decimal places. That's 0.1061. Now with that, we can now then use that to compute for this, because to compute for this, we need the z-scores of 6.8 and 7.1. So the z-score of 6.8 becomes 6.8 minus 7 over 0.1061. Well, the z-score of 7.1 is 7.1 minus 6.8 over 0.1061. Computing for this, we get a z-score for 6.8 of negative 1.89, and for 7.1, 0.94. Hence, this is the same as looking for the probability that the z-score is in between negative 1.89 and 0.94. Since we are done discussing the normal distribution, you should know already how we will deal with this one, and the answer that we get here is actually 0.7970 or 79.70%. Hence, the probability that if you take a lot of random samples with size 8, the probability that this means will fall between 6.8 to 7.1 would be 79.70%. There we go. Now, what would happen if we do the same thing, but this time the sample size is 20? Because that's what's asked in letter B. If a random samples of size 20 were taken, what proportion of the sample means would have a release pressure between 6.8 to 7.1 bars? Let's just place it down here. So in letter B, this time it's sample size of 20, but we're asked to find exactly the same thing. So first, we compute the standard error. So the standard error for this would be, we have the population standard deviation is 0.30 over the sample size, the spread of the sample size, which is 30. Therefore, we're going to get here a rounded up to 4 decimal places, 0.0671. Now, with this, we can now compute the z-scores of 6.8 again and 7.1. Which would be different because now we have a different standard error to use. So now 6.8 minus 7 over 0.0671, and then 7.1 minus 7 over 0.0671. So now we get the z-score. This time, the z-score of 6.8 is negative 2.98, while the z-score of 7.1 is 1.49. And in comparison to the sample size of 8, more or less it's farther from the original place, which would mean you can actually cover quite a lot more, or it might include a lot more. So in this specific case, we are now looking for the probability that the z-score is in between negative 2.98 and in between 1.49. So we already know how to do this, so we're already going to give the answer of where is it? Oh, there you go. We're actually going to get 93.05%. So therefore, the probability that the sample means, if your sample size is 20, the probability the means of those random samples is in between 6.8 to 7.1 has a higher probability, 93.05%. So if your sample size is 20, there's a higher chance that the mean is between 6.8 to 7.1 than your sample size of 8. And that is the sampling distribution of the mean.